Kids, time to do some applications of this stuff. Density, moment, center of mass, and surface area. Now, I am just going to really use density and moments to get to center of mass. So most of your questions that I would ask you on an assessment or for homework would be either a center of mass or surface area question, but we need these to get to the center of mass. So these three things were in section 15.5, and surface area is in 15.6. So we're going to cover them both today. Woohoo! All right, about to do a notes dump on you. You ready? Bam. All right, you don't need to write all of this down, but I do need you to get the idea of a lamina. So a lamina, think of as like almost like an amoeba looking thing, where it does have a thickness, but we're going to consider that it's so thin that it's two-dimensional. So maybe think of right, this shape right that is here. And it does have some thickness, but we're going to consider it infinitely thin. So that's why we're going to consider it two-dimensional. But we're going to say that it doesn't have a constant density. So we're going to normally you probably know from physics, right, that normally density is mass per volume. So your units might be something like kilograms per meters cubed. But again, we're going to consider that this is so thin that we're going to consider density in units. It's mass per area, right? So we're going to kind of reduce this exponent to meters squared. And we're going to pick some random point inside of here. And we're going to say that its density is described by this function rho. Right? Sometimes you'll see it kind of like curly like this. I think that's how you spell the letter, rho. xy, where the density function is continuous. And you're taking the limit as, right, the change in the mass compared to the change in area. And I think in somewhere in physics, I don't know, I have to ask Mr. Getz in physics, they do a similar, instead of rho, they call it sigma, and they call that charge density. So we're taking the mass and the area of a very small rectangle in here, contains the point xy, and we're going to take the limit as the dimensions of that rectangle approach 0. Oh my gosh, why did I type a little O instead of a 0? So here is a formula that you need. We're going to have variable density through that lamina. And to calculate, right, to sum all of those, that expression up, right, that Riemann sum, we're going to Leibniz it. I like to call this D for domain, but it doesn't really matter. But notice we're multiplying, right? The double integral is a product, and is a product of mass per area, right? So for instance, we might have had kilograms per meter squared, and then you're multiplying by the change in the area, which is meters squared, which means this just comes out with mass, kilograms, right? It's analogous to what we did in Calc 1, where we talked about, hey, if you had a function on the y-axis, you had meters per second, and your horizontal axis was second. seconds, and the area under the curve of this velocity function was distance, right? Because you took the integral of meters per second times seconds, right? And you got meters. So that's what we're doing here. So, for example, if I give you a triangular lamina and I tell you the vertices and I tell you the density function. So the density in this triangular lamina varies by the product of the x coordinates. Find the total mass. So let's draw this first. So I have 0, 0, 0, 1, and 1, 0. So there's my triangular lamina. And they're telling me the density in this lamina varies with the product of x times y. So think about what that means, right? Certainly at the corners, right, where you have 0, 0, the density is 0 at the corners, but isn't the density along the whole edges of this lamina here 0? Right? Can you see where the density would kind of be the highest? Right? The density is going to kind of rise up. Oh, I can't really draw this. But it's going to, right, be like here, right? Your highest, is that your max x, y there? So by this definition, what is my total mass? My total mass is the double area of the density function. And then I can draw either vertical or horizontal strips through there. I don't think it's going to matter. I just chose to do dy first. But what are my limits going to be? Since I put x last, I'm going to be drawing vertical strips through here. So I have 0 and 1. And since I have dy on the inside, y is going to go from y equals 0 to y equals what? Negative x plus 1, right? So to integrate this, right, is some of our old right, what we learned from double integrals. So I'm integrating with respect to y. So x is just a constant. So it's xy squared over 2, evaluated at y equals 0 and y equals negative x plus 1. Minus 0, right? But when I expand that out, I get x over 2 times x squared minus 2x plus 1. And so that ends up being 1/2 times x cubed minus 2x squared plus x. And that I am going to integrate dy, right? I'm sorry, dx. So I get 1/2 x to the 4th over 4 minus x cubed over 3. Don't forget your coefficient of 2 plus x squared over 2. At 0 and 1. So of course I'm going to be able to plug in 0 and everything's going to go away. For the second part, so I just have the first part of 1/4 minus 2/3 plus 1/2 when I plug in 1. Get a common denominator of 12. And this is 1/2 times 1/12 when you're done with that. common denominator work. Whoops. And I get 1 over 24. Okay, the total mass. All right, so as interesting maybe as that is, and that one wasn't so bad, like I said, I probably won't ask you for this question, and hopefully by the time we get through the next question, you see why. Oh my gosh, some more notes. Again, don't write all of this down. Let me just, it's all important, but there's some key points here. Pun intended. The moment. Now, if some of you have taken, I think you've done some of this work in IB Physics 1, if you're in the, if you've done that, or if you were in AP Physics, you've also done some of this work, just without the double integrals probably. So a moment of a point about an axis is the product of its mass and a distance. From an axis. So if I have my lamina, let's suppose I have it, let me just draw it in the first quadrant here. So something like this. And I pick a point. And then I pick an axis. Let's say I pick this line, x equals a. So I want to think about the distance of this point to this axis, right? Well, what is that distance? Right? Aren't we really just talking about, right, a y distance, right? Because the change in, an x distance, because the change in y is constant, right? What if I choose a horizontal axis? Right? What is the distance? Let's say that's y equals a. Right? The distance from this point to the horizontal axis is just a change in y, right? To find the moments of the lamina, generally we talk about the distance to the x and y axis. So what is a in both of those cases? Right? Wouldn't they be 0? So what we call the moment about the x axis, right? So an x axis, think about this y equals a being down here. Instead of any horizontal line, we're going to say y equals 0. So around the x-axis, we say it is a product of the mass, and then look at what we said the mass is, right? Forget all these stars and these little subscripts. Don't let that throw you. Just think about the mass, but the mass is this density times area, right? And then you're going to talk about, right, this y distance. And again, since we're just talking about the point, we're just talking about the point to the x-axis, excuse me, where y is equal to 0. So that distance is just y. So it is the product of mass, here's your mass, times that y distance. Distance from x-axis. That's called the moment, right? That's one of the moments. There are 2 moments. So here's our other moment, mass times a distance. So here again is the density times delta A times this x value. So remember now, we're not talking about just any vertical axis, though we could. We generally talk about the x-axis. So what is this distance? This distance is just x, right? 0 to x. So notice that there's approximates here because we're going to do this for all points, right? So we're going to sum all of these up. So these are the formulas that you need. Still don't even write this down just yet. The moment about the x-axis of the entire lamina, right? Moment x is this limit, Riemann sum, which we write as Leibniz. Notice that the moment in the x direction, or to the x-axis, has this y. It is a product of y, distance to the x-axis, density. The moment about the y-axis is, again, distance times density. Well, times mass, I should say. Your density function, dA, is your mass. Distance, mass. So, of course, it is a product, so it doesn't matter where you put the y, where you put the x. So here's the formulas that you need to write down. Moments, and really it's just the one box. Really, this is the one that you need to know. And what this is, the moments of mass are your center of mass, your center of gravity. So if you think, here's my lambda, here is your average x, average y. That is your balance point. And notice that, right, for each of these, we have the double integral of the product. Y times mass, x times mass. Please be careful down here with x bar and y bar, right? The x coordinate comes from the moment of y, right? But notice these, it almost is like not worth remembering these subscripts. If you just remember the double integral with x goes with, right? The one that has the x in it goes with x bar, and the one that has the y in it goes with y bar, okay? So I might not even remember the formulas that way. I might remember the formulas this way. X bar, y bar is equal to, and this is 1 over m. This is like average value, right? X that's xy. I'm sorry, that's x bar. Y bar, also average value, y. That's x bar and y bar. So before we compute this, I want to watch a little bit 5-minute video over here. It says 8 minutes, but we're not going to watch all of the 8 minutes.
Anderson, and this is AP Physics Essentials, video 95. It's on the center of mass. I want you to take a look at this tire for a second, and I'm going to apply a force to it. You can see the motion is fairly regular, and the reason why is that the center of mass is right in the middle of that tire, and it's rotating around that center of mass. Now let me apply a force to a hammer, and you'll see that the motion is not as uniform. It's tricky to our eyes, and the reason why is that the center of mass is off-center. What I'm going to do, though, is keep the center of mass where it is, and then I'm going to rotate that hammer, and you'll see that the center of mass stays where it is.
Pretty
It's
cool,
just the
right?
motion of that object above and below the center of mass that fools your brain. Now let me show you a system. So this is a Saturn V rocket. It's made up of a number of different stages. And so where would you say the center of mass is, the average mass? Well, it's maybe somewhere like that. What do you think would happen to the center of mass if I were to break this rocket apart into its two stages at this point? Well, it will stay in the same location. And so if we don't have an external force acting on the system, the center of mass stays where it is. Even though that might be rotational motion as we break those stages apart, the center of mass remains where it is. And so any system is going to have a center of mass, and that center of mass is made up of all the objects within the system. And what's neat about physics, according to Newton's second law, is if we don't apply a net external force, then there's going to be constant velocity. In other words, we're not going to have acceleration in that object. It'll either remain still, the center of mass, or it's going to move with a constant velocity. And so how do you figure out where the center of mass is? Well, a good place to get started is with a simulation. And this is Center of Mass Builder from SimBucket. And what you can do is you can click on the screen and it starts to make mass. It'll then show you where the center of mass is.
Right,
so you can see if I make a uniform mass, center mass is right in the middle. What happens if I add another uniform mass in the x direction? It's right between the two. What if I move in the y direction? You can see that it's going to be the average of that as well. So the center of mass doesn't have to be within a specific object. What's neat is you can use the hang test in physics. So if we simply hang this object, if we let it settle out, the vertical line through that hanging point is going to go right through the center of mass. So you can calculate the center of mass experimentally, and I'll show you how to use an equation to do it a little bit later in the video. And so if we apply a force to an object, we can get what looks like irregular motion in this hammer. But since we've applied a force, we know that we're going to have constant velocity. And so if I mark where that center of mass is, slow it down, watch what happens. We're going to have constant velocity. And that movement above and below that center of mass is confusing to our brain. And so let me show you how this works with a little video. I've got two pieces of ice that are connected together with a spring. I'm going to apply a force to one, and they're going to slide across the ice. And so we get this caterpillar-like motion. So to our brain, it looks like we're having acceleration and deceleration. But what I want you to do is get involved.
If you do this,
I want you to hold your finger on the screen where the center of mass is as I play this video. Where would that center of mass be? It's going to be on the spring right between those two blocks of ice. And so what you're going to try to do is, as I play the video, keep your finger between the objects on the spring. And so let's do that.
What happens?
So
right? When you keep your finger on there, look.
And you should find that as you trace it, you're showing movement from left to right with constant velocity. It's slowing down at the end a little bit. Now let's try a little harder one. We've got a force on both of these bricks on either side. So again, what you're trying to do is hold your finger in between those two bricks on the spring itself. So let me play this video.
Looks crazy, right?
And I'm doing this as well. So what I'm finding is that it's not moving as quickly, but it's still moving with constant velocity from left to right. And we could do even a complex system like this. We have 4 objects that are connected together with springs. So try to hold your finger where the center of mass is.
Right there in the middle of that
all 4
diagonal
of these objects.
spring.
If you
purple
do
one.
that, it's hard to kind of keep it in between all 4.
But look, your eyes try to get distracted.
Again, what am I finding? There's crazy motion on the screen, but my finger is moving across with constant velocity. And that's because there's no external force. And so we could look at a rocket. As a rocket flies through the sky, it takes a parabolic path like that. So we could trace it out and it would look like that. But let's say we were to take that same rocket and it were to fly through the sky, but halfway through it were to break apart into its 2 different parts. So it looks odd. In other words, that motion looks odd as it breaks apart. But if we were to plot the center of the mass it would follow the same parabolic path of that
Crazy.
rocket by itself. And that's because we have no external force. And so what's neat about the center of mass is you can take systems that are incredibly complex, and if we just figure out where the center of mass is, it makes solving that problem much easier. So as you move into AP Physics 2, you'll have to calculate where that center of mass is. And so if we have this object right here,
All
so we
right,
have
so we're not going to go into more physics, but this is what you're basically, right, you're what we're doing, right? We're finding that center of mass. Pretty cool that when you're doing projectile motion, right, when you're getting the path really of the center of mass, right, the center of gravity. Pretty cool. Hey, also another cool fun fact, if you think about like you can Google this. You can find the center of the mass of the United States. Maryland is pretty cool, right? Maryland is a very weird, right? This weird shape. I can't even really draw, something like that. That kind of now looks like Florida, but you know what I'm saying. If you considered that Maryland was this flat lamina and you had a function for its density and you calculated its center of mass, you'd be pretty darn close to Rockville. Isn't that cool? All right, so let us think about, though, what we would have to do to calculate this. If I give you a problem, right, if you're looking at this, I got so excited, but if you're looking at this and I ask you for the center of mass, how are you going to start this problem? There's one double integral because you have to divide each of these other double integrals by the mass, which is itself a double integral. So how many double integrals do you have to compute? Well, you have to do one for the mass, then you have to do two for the delta, for the x bar, and three for the y bar. So that's pretty freaking annoying, right? Come on, man. Do you see why I don't have to ask you a strictly mass question? Because I can test. You're going to have to find them. You're going to have to find the mass here. So sometimes this is another example of where I might not need you to actually go all the way through the integration. I might want to just ask you for the setup. So find the mass and the center of mass for another triangular lamina. I just changed up the vertices a little bit, and I changed the density function. So I need to find the mass first, then I need to import this into finding the center of mass, where I have to find the second and third double integrals. Okay, so again, let's start off drawing our shape. It's probably a little off scale there, but get the idea. So I need to first find my mass. So my mass is the double integral of my density function, d delta A. And again, I think you can see that it doesn't really matter whether I do vertical or horizontal strips. So again, I just kind of default to dy dx. So that means that my x limits of integration on the outside, 0 and 1. My y on the inside goes from y equals 0 to what? 2 is my y-intercept, and then my slope is -2. Right, so integrating on the inside first with respect to y. I'm going to get y plus 3xy plus 1/2 y squared. Evaluated at 0, which is nice because that will, since I have y's everywhere, I will only really have the first one. And at 2 minus 2x. So in place of y, I'm going to have 2 minus 2x plus 3x, 2 minus 2x plus 1/2, 2 minus 2x, all squared. And I'm going to write square, combine, get stuff together, blah, 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 and put in 0 and 1. And I want you to just trust me, and I'm going to tell you that you're going to get 8/3 out of that. What do I do with 8/3? So that's 1, finding the mass. So I've done this. But now to find x bar, I need to take 1 divided by 8/3 times the integral of x bar goes with x times my rho function keeping my same limits of integration. This integral actually turns out very nice. And this 1 divided by 8/3 is just 3/8, and that is actually what I got here. And then when I did y bar, one over the mass times the double integral y times 1 plus 3x plus y, and I will leave this integration to you as well and tell you that what I got out of this was 11/16. So the center of mass is the point 3/8 comma 11/16. So go back to your picture and make sure that's reasonable. Does it look like you can balance that lambda of varying density? Do you buy, right? 3/8 is a little shy of a half, and 11/16, right, is a little more than a half in that direction. So somewhere up there, given this varying density, there is your balance point. And it is within the region, so I feel pretty good about myself. All right, so every time I ask you for a center of mass problem, you really have to do 3 integrals. Okay. So you hope I don't ask you too many of those, right? All right, let's do surface area. Surface area really is, right, very similar to length of a curve, right? Arc length, where I developed this formula for you in BC, and we talked about how it came from a whole bunch of infinite hypotenusae, right? Very similar situation. Notice that instead of dy dx, I have partials. So I have a surface up in z space that is, its domain space is xy, where every xy are within this region D, on or in the xy plane. And then the surface area is just a square root Pythagoras looking thing with your 1 here, right? dz over dz. 1 plus your partials with respect to x and with respect to y. So find the surface area of the portion of the surface. What is that? that lies above the region D in the XY plane, and they've given me, this is my X and my Y and my Ys, right? So what does that look like? So in general, before I start to attempt poorly, as you well know, to draw this, what we're doing with surface area, 3D surface area, is saying that we've got some region in the XY plane, and we have some surface up here, and we are mapping this whole region up to this surface. It's not very good. And we call this is the surface that we want to find the area of. Okay, the portion of Z. So first, can you think about what this might look like? What it does look like? Well, maybe if I square both sides and then move the x squared over. Right, can you tell what that is? Yeah, right? It's a cylinder that we're gonna kind of chop off, right? So again, I'm going to attempt a very poor drawing here. You guys are so much better at this than I am. Seeing your drawings, right? Y is going to run free. Right, and I cut it off at the XY plane, right? I didn't go down around it. Now, but I have the region D down here that goes from 0 to 1 and 0 to 4. So I kind of have, here's this rectangular region down here. And we're mapping it up to the top of this surface. And that's what I want to find the surface area of. Okay, all the points from here are being projected up onto this cylindrical, really poorly drawn thing there. So the surface area is going to be what? I need partial z, partial x. Right, so what do I have? Partial, so let me work over here. Z is equal to 4 minus x squared to the 1/2. So partial z, partial x. Don't forget the chain rule. So the 2's are going to go away, and I'm left with negative x over the square root of 4 minus x squared. So that's going to go in here. And then what's partial z, partial y? 0, right? Because there is no y, so that's just 0. Now, what are my limits of integration? since I have nothing but x stuff in here, I probably should integrate dx, right? First, and then dy. And since dy is on the outside, I mean, I guess it doesn't really matter. But if with y on the outside, I'm going to put 0 and 4 here. X on the inside, I'm going to put 0 and 1 there. And now I've got some math to do. So this is here, the square root of 1 plus negative x squared is x squared. And the square root of 4 minus x squared is just squared, is 4 minus x squared. But so I need to get a common denominator. So I'm going to have 4 minus x squared over 4 minus x squared plus x squared all on top of 4 minus x squared when I get a common denominator. My x squareds in the numerator are going to go away, and I'm left with 4 over 4 minus x squared. What am I going to do with that? Oh, well, you know what I can do? I can make that, I'm going to erase this, so let me let you get a look at that before I erase it again. Didn't leave myself a whole lot of space down here. All right, so let's see what we got. So I am integrating 0 to 4 and 0 to 1, the square root of 4 over the square root of that thing, right? But the square root of 4 is just 2. Now, what am I going to do with that? So do you recognize that at all? Maybe, kind of, sort of. What is this integrand? I can't just integrate with u substitution, right? I can't make 4 minus x squared u because my derivative is negative 2x and I don't have an x thing floating out here. But with a little algebra, and we did problems like this in BC, little fancy factor the 4 out, and you get 1 minus x over 2 squared. Factor the 4 out here. 4 over 4 is 1. X squared over 4 is the same as x minus x divided by 2 squared. Take this 4 out here, and it becomes a 2, which means you are integrating now. Can you tell me what integral formula you're going to use if you haven't recognized it yet? Yep, that's going to be inverse sine. With a u substitution, right? So I'm going to end up with this 2 on the outside, the 0 and 4 still, and then I'm going to have inverse sine of who? Evaluated at who? Right? So this ends up to be 2 inverse sine of 1/2. And inverse sine of 0 is 0. Now let's integrate this so I can now say this is integrating dy. I could take that pi over 6 out there too, couldn't I? So plug in 4, and I get 4 pi over 6 or 2/3 pi minus 0. The surface area of that poorly drawn shape that I had there before is 4 pi over 3. Whoosh, woo! All right, congrats for getting through all of this. And I will see you at our live session.